Welcome back. In this video, we are continuing to look at rational functions, and we're actually going to see that the poles that we find can be classified as one of two things, either a vertical asymptote or a hole. And so we go through this video, we are going to look at one example and kind of talk in depth about that example. So the function that we're going to work with is the function x squared minus 4 over 2x minus x squared. And so if we want to find its poles, right, we know that we need to take the denominator, 2x minus x squared, and say that it can't be 0 or set it equal to 0 and just remove it either way. But when we do this, we can factor it. I'm going to pull out a minus x, and then I'd have a negative 2 plus x. And I did that mainly so that I could rewrite it as x minus 2. Okay. Um, you'll see why later on. But I'm choosing to write it like this, and then from this I can see that negative x would equal 0 or couldn't be 0, or x minus 2 can't be 0. And so I'm finding the poles. And so x cannot be 0, x can't be 2. So I'm going to say these are the location of the poles. Okay. So there's a pole at 0, there's a pole at 2. All right, fine. Okay, now we actually didn't take the numerator into consideration, and do we really need to? So I have the factored form of the denominator here, but let's factor the numerator and see what happens. So if I do factor that, it'd be x minus 2, x plus 2, because it is a difference of squares, over negative x, x minus 2. Oh, okay, well now that I factored completely, right, I could say, oh, let's cancel this. And that's the number one mistake that students actually make. We don't want to cancel these just yet. We want to leave it as in completely factored form for a while. Okay, but eventually can we cancel? Yes, we certainly can. All right, but because we want to cancel the x minus 2's, there's a special behavior that happens. We get, instead of well, so there's still a pole at x is equal to 2, but it actually ends up being a hole because we cancel that factor out completely. And that's exactly what the definition says. So if we look at simplifying here and we make that simplification and we end up with x plus 2 over negative x, the canceled factor, if it cancels out completely, that is a hole. And what we are left with at the end, the resulting simplification, we call r of x for a reduced function. Okay, and so then this hole, we know it occurs at x is equal to 2. So for our instance, we have a hole with so we have a hole at the point 2, and then I would need to put in 2 into r of 2 according to the definition to find out the location of the hole. And so if I do this 2, and then this would be, 2 plus, 2 plus 2 over negative 2, what would that give me? 2 comma, let's see, 4 over negative 2, negative 2. So I would have a hole at this point when I go and graph the function. Okay, so point being, a pole can be a hole, okay? And then what about 0? What happens there? Well, there's not another fun name for that other than it's called an asymptote. Okay. Informally, when you think about an asymptote, all it means is it's a line that you approach in the long run. Okay. And so this is some line. I should actually clarify, this is some line, right? It's some line that you get close to as you get away from the origin. Okay. Locally near the origin, weird things can happen, but in the long run, as you get away from the origin, you get close to this line, this asymptote. And so we do encounter two types of asymptotes in this course: vertical, and then you're going to guess the other one is probably horizontal. You're going to be right, but we'll talk about horizontals later on. But when we talk about vertical asymptotes, it is a line of the form x is equal to c. So then when we look at a graph, okay, I'm going to say, okay, here is C. I don't know what it is, but it's a line. This is the x value, and it's all along here. Okay, this is the line x is equal to C. And let's see what the definition says. If f of x approaches positive or negative infinity as x approaches C from either side. So you could do something like this, and this, like you could go up on both sides. You could go up on one side and down on the other. You could flip them around. Down here, up here, and erase this, right? You could go down on both sides, okay? Any variant thereof, but bottom line is as you go down, so was just a quick sketch, but if you were to get closer to the vertical asymptote, you would get closer to it and extend away from the origin. Okay, so approach plus or minus infinity as you go on either side. Okay, so now what we didn't emphasize was the second part of the definition. Vertical asymptotes occur at poles of the reduced form, R of x. Okay, so we had R of x as this. Oh, okay, we said the poles were 0 and 2 for the original function, but we said 2 ended up being a whole. So then the remaining pole is the location of a vertical asymptote. Okay, so we have a pole at that, which is a vertical asymptote. So in our graph, okay, so our example, what we would see is something like at 0, we would have this vertical line along the y-axis, but that's the line x is equal to 0, right? And then I don't know what it looks like yet, but we're going to do some sort of hugging behavior, and we also know that 2, we're at -2. We have a hole there. But we have something like this maybe going on. I don't know if it goes up or down yet. We'll figure that out. But I at least know there's a line here at x is equal to 0 that I can't cross. And I have a hole at 2, -2. Okay. Now, just to kind of summarize like how we classify a pole as either a hole or a vertical asymptote, this flowchart I find to be very handy. Okay, so first we factor. Okay, then we find the poles in the domain of the original function. I didn't find the domain, but we could, right? And then simplify, but only, notice this is only after you state the domain and the poles, okay? Simplify after, okay? And then find the poles in the reduced form of poles and domain of the reduced form. And then any poles of the reduced form are vertical asymptotes. Okay, that's what remained. And then poles that cancel completely from f of x in going to r of x, those are locations of holes. Okay, so that's the flowchart that I recommend in using to kind of process, the poles that I have, are they vertical asymptotes or holes? So I didn't follow it completely, but again, after finding the poles, I could have said, okay, the domain is negative infinity to 0, union 0 to 2, union 2 to 0, or 2 to infinity. And then r of x, this has domain negative infinity to 0, union 0 to infinity. Okay, 0 was still present in the reduced form, so that was our vertical asymptote, right? 2, the pole of 2 ended up canceling out, so that was when we had a hole. Okay, so again, this flowchart, pretty useful, at least in helping us decide what happens at each of the poles.